Hi dear children, welcome to today's class. Today we are going to continue exercise 12.3, 8th question. Figure 12.26 depicts a racing track whose left and right ends are semicircular. The distance between the two inner parallel line segments is 60 meter and they are each 106 meter long. If the track is 10 meter wide, find the distance around the track along its inner edge, the area of the track. First we need to find out the distance around the track along its inner edge. Okay, so the given informations are the left and right ends are semicircular. The left and right ends are semicircular. The distance between inner parallel lines, that is the distance between this BC and EH, that is 60 meter, and the length of that parallel lines, that length of BC and length of EH, that is 106 meter, then obviously the length of AD and length of FG, that is also 106 meter. The width of the track, the shaded portion represents the track. The width of the track, that is 10 meter. Okay, so this much of information is given in this question. First we need to find out the distance around the track along its inner edge. For that, the inner edge, that is B, C, Q, H, E, P. Okay, B, C, Q, H, E, P. That is our inner edge. We need to find out the distance. Okay, that is distance is equal to BC plus, then we have CQH. That is actually, since we have circular ends, this CQH is a part of semicircle. Okay, actually CQH is the circumference of a semicircle. Okay, so plus circumference of the semicircle CQH plus HE, and this end is also circular, therefore this EPB, that is also the circumference of a semicircle, plus circumference of semicircle EPB. Okay, circumference of the semicircle EPB. This is equal to BC length is given on the question, that is 106, plus circumference of the semicircle. Okay, so half into 2 pi r, that is our formula. Then what is the radius of that circle? Inner edge, circular end, the radius CH, that distance. Okay, distance between inner parallel lines, that is 60 meter. That means this CH is 60 meter. Okay, that CH is or CH or BE. Okay, we have two circular ends. The CH is 60 meter and BE is also 60 meter. Actually, they are the diameter of that semicircles. This BE is the diameter of the semicircle EPB, and CH is the diameter of the semicircle CQH. Okay, that length is 60 meter. Therefore, the radius of these semicircles is equal to 30 meter. So, into 30 plus HE, that is 106, plus the circumference of the semicircle EPB. Since it is semicircle, we will have half into 2 pi into here also the radius is 30. And this is equal to 212 plus half get cancelled. We will have 30 pi. Here also we will have 30 pi, that is 60 pi is equal to 212 plus 60 into 22 by 7. This is equal to, after all the simplifications, you will get 2804 divided by 7 meter. 2804 divided by 7 meter. Okay, this is the distance around the track along its inner edge. Now, second question, we need to find the area of the track. Actually, the area of the track, that is equal to the area of the shaded region. Area of the track equal to area of the shaded region. Okay, so area of the track is equal to area of the shaded region. Okay, now just look at that figure. In that shaded region, we have one rectangle ABCD and we have one more rectangle EFGH. That means in that shaded region we have two rectangles ABCD and EFGH. The length of that rectangle is 106 and the breadth is 10 meter. Similarly, the length of the rectangle EFGH, that is 106 and the breadth 10 meter. Okay, so we can find out the area of that two rectangles. And in left and right we have circular ends. So we need to find out the area of the shaded portion in left and right ends. Actually, that is area between two semicircles. That is area between two semicircles. Okay, on both sides we have same semicircles. So just look at here. Here we have one semicircle BPE. Okay, we have one semicircle BPE. That is our inner semicircle. And the outer semicircle ARF. Outer semicircle ARF. So inner semicircle BPE and outer semicircle ARF. So we have two semicircles, inner semicircle and outer semicircle. And what is the radius of inner semicircle? That we already discussed. This BE is the diameter of that semicircle and that length is 60 meter. So the radius 30 meter. And what about that outer semicircle? Outer semicircle, actually that diameter is AF. Diameter AF. AF we can write it as AB plus BE plus EF. Okay, AF we can write it as AB plus BE plus EF. AB length 10 plus 60 plus 10, that is 80 we will get. So this AF is equal to 80. AF we will get it as 80 and that AF is the diameter of our outer semicircle. AF is the diameter of our outer semicircle. Therefore, the radius is equal to R is equal to 40 meter. Okay. So if you consider this end, there also you will get the radius of the inner semicircle 30 and the radius of the outer semicircle you will get it as 40. Okay. Now, area of the shaded region, that is area of rectangle ABCD plus area of rectangle EFGH plus, okay, we left end and right end we have circular ends, and now we know that the radius of inner and outer semicircle in left and right, they are equal. Okay, so we can write it as 2 into 2 times 2 into. Now, how can you find out the area between two semicircles? That is actually area of outer semicircle minus area of inner semicircle. Area of outer semicircle minus area of inner semicircle. So that is area of semicircle, with a radius 40, that is our outer semicircle with radius 40, minus area of semicircle with radius 30. Area of semicircle with radius 40 minus area of semicircle with radius 30. Okay, and this is equal to, what is the area of ABCD? That is a rectangle. So we will have length into breadth, right? Length into breadth. That is 106 into 10 plus, again here we have 106 into 10 plus 2 into area of outer semicircle. Since it is semicircle, we will have 1 by 2 pi r square, 40 square minus 1 by 2 pi into 30 square. This is equal to 2120 plus pi into minus 900. Okay, 1600 minus 900. That is equal to pi, we need to substitute it as 22 by 7. This is 700 into 700. After all the calculations, you will get it as 4320 meter square. 4320 meter square. Therefore, the area of the track is equal to 4320 meter square. Now, we are going to do the 10th question. The area of an equilateral triangle ABC is 17320.5 centimeter square. With each vertex of the triangle as center, a circle is drawn with a radius equal to half of the length of the side of the triangle. Find the area of the shaded region. So, this is our figure, and that ABC is an equilateral triangle. Since that ABC is an equilateral triangle, that angle A is equal to 60 degree. Okay, since ABC is an equilateral triangle, angle A is equal to 60 degree. Okay, now we don't know the length of the side. We don't know the length of the sides of that equilateral triangle. Let it be A. That length is equal to A centimeter. But we know that the area of an equilateral triangle is root 3 by 4 into side square. That is equal to, that value is given in the question, that is 17320.5. 17320.5. Now, root 3 by 4 into A square is equal to 17320.5. Now take this 4 into RHS, then root 3 by into A square is equal to 17320.5 into 4 we will get. The value of root 3 is given in the question. Then just substitute that value, 1.73205. A square is equal to 17320.5 into 4. Okay, now this we can write it as 17320.5 divided by 1, and here after the decimal point we have 1, 2, 3, 4, 5 places. So just put 5 zeros. Okay, into a square is equal to, here we have only one place, so we will divide it by 10 into 4. Okay, now on both sides we have 173205. Just cancel it. Then we will get a square divided by 100,000 is equal to 4 by 10. 4 by 10. And this you will get it as a square is equal to 4, after that 4 zeros, 40,000 you will get. A square is equal to 40,000. Then a is equal to square root of 40,000, that is 200 centimeter. Okay, so we got the length of the side of that equilateral triangle ABC, that is equal to 200 centimeter. Now, actually we need to find out the area of shaded region. What is the area of shaded region? Area of the shaded region is actually, this is a sector subtended angle 60 degree. Okay, that is a sector subtended angle 60 degree. So we have such three sectors are there. So actually this area of the shaded region, that is equal to area of the equilateral triangle, area of the shaded region, area of the shaded region is equal to area of triangle ABC minus area of three equal sectors with angle of each sector 60 degree. Okay, minus 3 into, we have three sectors, 3 into area of sector with angle 60 degree. Area of triangle ABC, that is given in the question. So just substitute that value, 17320.5 minus 3 into theta divided by 360 degree into pi r square, that formula. So 60 degree divided by 360 degree into pi into, okay, here the radius that is given in the question, the radius of that is equal to the half of the length of the side. The radius of each circle is equal to the half of the length of the side. Okay, length of the side, that is 200. Then the half of that is 100 square. Okay, so the radius of that each circles is equal to half of the length of the side, that is 100. So we will get it as 17320.5 minus 3 into 1 by 6 into pi into 10,000. Okay, and this is equal to pi. Here we need to substitute it as 3.14 because that is given in the question. Use pi is equal to 3.14. And this is equal to 1620.5 centimeter square. 1620.5 centimeter square. Okay. Therefore, the area of the shaded region is equal to 1620.5 centimeter square. Now, we are going to do the 13th question. In figure 12.31, a square OABC is inscribed in a quadrant OPBQ. If OA equal to 20 centimeter, find the area of the shaded region. OA is given and this OABC, that is a square OABC. This is our figure. Then OABC is a square and OPBQ, that is a quadrant. And OA, that length is 20 centimeter. That much of information is given in this question. Now we need to find out the area of shaded region. Area of shaded region. And before that we need to find this OB length. We need to find out that OB length. So consider this triangle OCB. Okay. Since OA is 20 meter and that OABC is a square, this OC is 20 meter and CB is also 20 meter. Okay. So OC is equal to CB is equal to 20 meter. And that is a square. Therefore, this angle that is 90 degree. So we can apply Pythagoras theorem. By using Pythagoras theorem, we will get OC square plus CB square is equal to OB square. OC square plus CB square is equal to OB square. OC 20 square plus 20 square is equal to OB square. And this is OB square is equal to, what you will get? 800 you will get. Then OB is equal to 20 root 2. OB is equal to 20 root 2 you will get. That OB is actually the radius of the circle. OB is actually the radius of the circle. So radius is equal to 20 root 2. Radius is equal to 20 root 2. Now we need to find out the area of shaded region. So area of shaded region is equal to, how can we find out the area of shaded region? In our question it is given that OPBQ, that is a quadrant. And now we know the radius of that circle, that is 20 root 2. And OABC, that is a square. So there's the area of the shaded region, that is equal to area of OPBQ minus area of OABC. Okay. OPBQ, that is a quadrant, and we know that a quadrant subtends angle 90 degree. Quadrant subtends angle 90 degree. So this is equal to theta divided by 90 degree divided by 360 degree into pi r square, r 20 root 2 all square. Okay. Minus 20 into 20 square. So the area of a square is a square, 20 into 20. And this is equal to 200 pi minus 400. That is equal to, in this question it is given that use pi is equal to 3.14. So this is 200 into 3.14 minus 400. That is equal to 628 minus 400 is equal to 228 centimeter square. Therefore, the area of the shaded region is equal to 228 centimeter square. Now we are going to do the 15th question. In figure 12.33, ABC is a quadrant of a circle of radius 14 centimeter and a semicircle is drawn with BC as diameter. Find the area of the shaded region. ABBC is a quadrant, that is given in the question. ABBC is a quadrant and we need to find out the area of the shaded region. Okay. So ABBC, this is our quadrant, and this BC, that is the diameter of the semicircle BQC. Okay, that is the diameter of the semicircle BQC, and it is given that this quadrant is the part of the circle with a radius 14 centimeter. That is given in the question. Now what we are going to do is, first we need to find out the length of BC. We need to find out the length of BC. Since that ABPC is a quadrant, this angle is 90 degree. So we can apply Pythagoras theorem in triangle BAC or ABC. Then we will get AB square plus AC square is equal to BC square. AB square plus AC square is equal to BC square. That is BC is equal to square root of AB square, that is 14 square plus 14 square. Thus you will get it as 14 root 2. Okay, so the length of BC is equal to 14 root 2. And it is given that this BQC is a semicircle with diameter BC. Okay, BQC is a semicircle with a diameter BC. Now, this is diameter, then the radius of that semicircle. Radius of semicircle is equal to 7 root 2, half of BC. 7 root 2. Now, area of the shaded region. Area of the shaded region. Area of the shaded region, that is equal to, area of the shaded region is equal to actually area of the semicircle. Area of the semicircle with radius 7 root 2 minus area of segment BPC. Area of segment BPC. Area of segment BP.